In this lecture, we show how one can adapt the fourth-order Runge Kutta method for first-order initial value problems, or IVPs, to higher-order IVPs. Let us first talk about the first-order initial value problem, where y prime equals f of xy, with the initial condition that y of a equals alpha. We are assuming that y equals y of x. For the fourth-order Runge Kutta method applied to this IVP, we set x sub 0 equal to a and y sub 0 equal to alpha. Let n be the number of subintervals for the interval from x equals a to x equals b. Using a uniform partition, if h is the step size, then h equals b minus a divided by n. Then a recursion for the fourth-order Runge Kutta method for this IVP is given by these set of equations. X sub I plus 1 equals x sub I plus h, y sub I plus 1 equals y sub I plus the sum of k sub 1, 2k sub 2, 2k sub 3, and k sub 4 divided by 6. K sub 1, k sub 2, k sub 3, and k sub 4 are given by these equations. I goes from 0 to n minus 1. To adapt this recursion to a higher order IVP, we can start by reducing the order of the IVP. We illustrate this with a second order IVP. Let y double prime be equal to f of x y prime, where f is differentiable up to fifth order. Suppose y of a equals alpha sub 0, and y prime of a equals alpha sub 1. We define a new variable u and set it equal to y prime. Then u prime equals y double prime, which is now equal to f of x y u. And so the differential equation becomes a matrix system with the vector with components y prime and u prime equal to the vector with components u and f of x y u. For the initial conditions, we have the vector with components y of a and u of a equal to the vector alpha sub 0, which is y of a, and alpha sub 1, which is y prime of a, or u of a. We call the vector with components y and u as the vector uppercase y. Because of this equation, the vector y prime is equal to some vector function which we call g of x, y, u. We set the vector y sub 0 equal to the vector y of a, which is the vector lowercase y of a, u of a, or alpha sub 0, alpha sub 1. Using the interval from x equals a to x equals b with n uniform subintervals and the step size h, we have the following recursion. X sub I plus 1 equals x sub I plus h. The vector y sub I plus 1 equals the vector y sub I plus the sum of uppercase k sub 1, 2 times uppercase k sub 2, 2 times uppercase k sub 3, and uppercase k sub 4 divided by 6. Adapting the formulas for the lowercase k sub j's from the first order IVP to the uppercase k sub j's, which are all vectors. The uppercase k sub j's are defined by the following equations. Uppercase k sub 1 equals h times g of x sub I, y sub I, u sub I, and applying the formula for g is equal to h times the vector u sub I, f of x sub I, y sub I, u sub I. Let the components of k sub 1 be k sub 1, 1 and k sub 2, 1. Adapting lowercase k sub 2 to uppercase k sub 2, uppercase k sub 2 is h times g applied to x sub I plus 0.5 h, y sub I plus 0.5 k sub 1, 1, and to u sub I plus 0.5 k sub 2, 1. Observe that we are applying to y sub I and u sub I their respective increments from k sub 1. K sub 2 should equal this vector quantity. Let the components of k sub 2 be k sub 1, 2 and k sub 2, 2. Similarly, the vector k sub 3 equals this quantity, which should be equal to this vector. Let the components of k sub 3 be k sub 1, 3 and k sub 2, 3. And finally, the vector k sub 4 equals h times g applied to x sub I plus h, or to x sub I plus 1, to y sub I plus k sub 1, 3, and to u sub I plus k sub 2, 3. k sub 4 should be equal to this vector. Let the components of k sub 4 be k sub 1 4 and k sub 2 4. We form a new matrix by taking each k sub j as the jth column of this new matrix. We can then rewrite the recursion for the y sub i's in the following way, and the viewer can check that the vector y sub I plus 1 u sub I plus 1 equals the vector y sub I u sub I plus 1/6 times the new matrix times the vector 1, 2, 2, 1. In general, for the mth order IVP, where the mth derivative of y equals f of x, y, y prime, etc., 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 all the way to the m-1 derivative of y, with the initial conditions that the kth derivative of y at x equals a equals alpha sub k, for k equals 0 to m-1, we introduce the new variables u sub 1, u sub 2, etc., 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 all the way to u sub m-1, where u sub k equals the kth derivative of y. The mth order differential equation becomes this matrix system of differential equations. In vector form, these are the initial conditions. This is now the vector y prime, and this is the vector g applied to x, y, u sub 1, etc., 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 all the way to u sub m-1. We abbreviate the notation for this quantity to g applied to x and the vector y. We set the vector y of a of initial values equal to the vector y sub 0. For the sake of the recursion, let the components of the vector y sub 0 be lowercase y sub 0, u sub 1 0, etc., 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 all the way to u sub m-1 0. Let the vector y sub I be equal to the vector lowercase y sub I, u sub 1 I, etc., 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 all the way down to u sub m-1 I. As usual, x sub I plus 1 equals x sub I plus h. The vector y sub I plus 1 equals y sub I plus the sum of the vectors k sub 1 to k sub 2 to k sub 3 and k sub 4 divided by 6. K sub 1 equals h times g applied to x sub I and the vector y sub I, and is equal to this quantity. We set this equal to the vector k sub 1 1, k sub 2 1, etc., 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 all the way down to k sub m1. The first index indicates the row of the entry, while the second index indicates the j value of k sub j. In this case, the entries are coming from k sub 1. K sub 2 this time equals h times g applied to x sub I plus 0.5h and to y sub I plus 0.5 k sub 1. Except for its last entry, k sub 2 looks like this. For the last entry of k sub 2, we have to evaluate f at x sub I plus 0.5h and at the vector y sub I plus 0.5 k sub 1. The vector y sub I plus 0.5 k sub 1 in coordinate form is lowercase y sub I plus 0.5 k sub 1 1, u sub 1 I plus 0.5 k sub 2 1, u sub 2 I plus 0.5 k sub 3 1, etc., 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 all the way to the very last coordinate, u sub m1 I, plus half the last entry of k sub 1, which is f applied to x sub I, y sub I, u sub 1 I, etc., 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 all the way down to u sub m-1 I. This last entry of k sub 1 is k sub m1. We set this equal to the vector k sub 1 2, k sub 2 2, etc., 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 all the way down to k sub m2. K sub 3 equals h times g applied to x sub I plus 0.5h and to y sub I plus 0.5 k sub 2. The viewer can check as an exercise that k sub 3 is equal to this vector. We set k sub 3 equal to the vector k sub 1, 3, k sub 2, 3, etc., 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 all the way down to k sub m, 3. K sub 4 equals h times g applied to x sub I plus h, and to y sub I plus k sub 3. K sub 4 looks like this. We set k sub 4 equal to the vector k sub 1, 4, k sub 2, 4, etc., 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 all the way down to k sub m, 4. Similar to what we had for the second order IVP, the vector y sub I plus 1 for the mth order IVP equals the vector y sub I plus 1/6 times the matrix of the k sub j's times the vector 1, 2, 2, 1. Writing out the individual recursions, x sub I plus 1 equals x sub I plus h, lowercase y sub I plus 1 equals lowercase y sub I plus the sum of uppercase k sub 1, 1, 2 times uppercase k sub 1, 2, 2 times uppercase k sub 1, 3, and uppercase k sub 1, 4 divided by 6. Similarly, u sub 1 I plus 1 equals u sub 1 I plus the sum of k sub 2, 1, 2 times k sub 2, 2, 2 times k sub 2, 3, and k sub 2, 4 divided by 6. We generalize this to the rest of the u sub r I plus 1s, where r goes from 1 to m minus 1. I goes from 0 to n minus 1.